Hello, everyone. Welcome back. Today, we're going to talk about testing claims about two proportions. And so our goal is, says, understand how to state hypotheses when testing claims about two proportions, and also be able to test claims about two proportions using the p-value method. The other value methods, including the critical value method and confidence interval method, but we're going to focus on the p-value method. So the idea of testing claims about two proportions is we want to see, trying to compare two proportions and see if they're equal or not. Or maybe one is greater than the other, or less than one of the other. And try to see if we can say with statistical confidence whether something is, whether there's some difference between them. For example, as a good example is population of people that takes one drug and one population that doesn't. Okay, so they often in drug tests use what's called placebo, where people are not actually taking the drug, though they don't know that. And the goal is to find out if the drug actually has an effect or not. And so, obviously, if it's a drug, you want to believe that the proportion, um, say, of people who actually get better, proportion of people who get better is higher with the drug than without the drug. So, hypothesis setup will be very similar, except this time we're comparing the hypotheses, or comparing proportions rather. So, our null hypothesis will be the proportions are equal. Then the alternate will be either that they're not equal, or that one is greater than the other or less than the other. Then the requirements are similar requirements we had before for proportions. These portions are from simple random samples, so they're not related to each other directly. And then the samples are independent, so meaning that's so not only random, they're also independent. They're not related to each other or connected to each other in any way. And also have to be at least 5 successes and 5 failures, then to be able to use the methods, the standard normal distribution methods. Now, let's come over here to the right and briefly discuss how we can also write these. So the way we've written them over here, that our hypothesis is also correct, but they can also be written in a slightly different way. Make sure that's clear. So your null hypothesis can also be written if you subtract P2 from both sides. You can also written as P1 minus P2 is equal to 0. That's the same thing. Simply subtract P2 from both sides. And then the other alternates, HA or H1, whichever way you want to call it, can also be written as P1 minus P2 is not equal to 0. So each one, I'm subtracting P2 from each one. Or you have HA, I should possibly just say in each case, or P1 minus P2. So for this one, once again, subtract P2 from both sides. P1 minus P2 is greater than 0. Or for the last one, P1 minus P2 is less than 0. Actually, StatCrunch also lists them this way. So just realize those are exactly the same. Okay. Now, so that's the way the hypotheses are set up. And also we're going to use StatCrunch. And so the method, the how do we get there is very similar to what we did before. So go to stat, proportion stats, and time and go to two samples, either with summary, if you have the summaries, if you have the actual proportions and sample sizes, or if you have the data, you can input the data for two samples. Now, also notice I'm not giving you the test statistic, and basically this is very complicated. And so essentially we're going to let the computers like StatCrunch or other programs like that to do that for us, to find those test statistics. Okay. And also should mention, if you haven't already, make sure you look back at the videos I've done before, the basics of hypothesis testing and also testing claims about a single proportion, because the method is essentially going to be identical, except our hypotheses will be stated a little bit differently. So let's take a look at our first example. This one, it says in the study of Burger King drive-through orders, it was found that 264 orders were accurate and 554 were not. For McDonald's, 329 orders were found to be accurate, while 33 were not. Use a 0.05 significance level. Test the claim that Burger King and McDonald's have the same accuracy rates. So what we want to do here then is let's kind of put in our values. And notice this time we have to be careful about the values it gives us. Let's call this for Burger King, BK, and McDonald's, let's call it MD. Okay, so our N here, now be careful with this because it says 264 orders were accurate and 54 were not. So that's neither one is the total number. Call this N1. So to get the total number, we just need to add those together. And so it's going to be 54 plus 264 and that's 318. So that's N1 is 318 total orders for Burger King. Then McDonald's, go and do the same thing while we're here. And so for McDonald's, it was 329 were found accurate and 33 were not, plus 33 is 362. And we can see right away that in both cases we have this, assuming these are independent, which assume it is, and they're independent, they're random. This meets the test, this meets the requirements we mentioned, at least 5 successes and 5 failures. Okay, now it doesn't actually give us the proportions, the p-hap1, we can find that. And the question is which ones are inaccurate. And here it actually doesn't say whether you want to think of this as being accurate or inaccurate. The accuracy rate, so we could just simply do the ones that are accurate over, so it will work either way. But so the accuracy is going to be 264 over 318. And let's find out what that is. And that's approximately 0.83 if I do 2 decimal places. And for P2 for McDonald's, the same thing. The accuracy is going to be 329 over 362. And that is going to be approximately, I said 329 over 362. And this, 2 decimal places, is going to be 0.91. You see, the samples are clearly different. The question is, are they statistically different? And that's what we want to find out. Once again, our alpha is it gives us is 0.05. Okay. Now, let's think about our hypotheses. Okay. So our H0 is going to be the same as in each case, is going to be that P1 is equal to P2, that both proportions are the same, that there's no difference between them. Okay. Now let's look at our claim for H1 or HA. And this says the claim that Burger King and McDonald's have the same accuracy rates. So actually, in this case, it turns out that our claim is actually the same as our null hypothesis. And since it doesn't mention one being lesser or greater than the other, then our alternate will just be that they're not equal. And remember, this also can be written as P1 minus P2 is equal to 0, and P1 minus P2 is not equal to 0. Okay. Now, so then let's do that, and let's use that information, then go to StatCrunch. And let me write down these values I need so we don't have to jump back and forth. Okay, let's then go to StatCrunch. Wrong thing. Okay, now so once again, go to Stat, just like we did with the testing one proportion. Then we go to proportion stats. This time we go to 2 sample, and once again, give us the option for with data or the summary. So if we're given the data, we can always input the data or have it inputted, then go from there. But here we have the summaries. And so here it gives us for sample 1 and sample 2. So here also you have to determine which one's your sample 1 and sample 2. And as long as you do everything correctly, it doesn't really matter. But in this case, we chose sample 1 to be Burger King. So the number of successes for Burger King was 264 out of the number of observations, which was 318. For McDonald's, sample 2, it was 329 successes, we're counting accurate order as a success out of 362. And then, yeah, so here, StatCrunch sets up our hypotheses that way. So does P1 minus P2 is equal to 0. And then P1 minus 2, the alternate one's going to be the 3 choices, not equal to, less than, or greater than. So this one choose not equal to. And then really that's all we have to do to compute. Okay. And once again, let me copy this, and we'll copy it and put it into our Word document. We can also close this and come back to it later. Okay, let's take a look at what we have. We don't have a lot of space here, but that's okay. Yeah, so it doesn't give us our, we actually have to find then, this summary doesn't actually give us the actual proportions, but we can do that on our own. Once we do that, then we take a look at what we have. And let's collect the information. I'll just write it over here. So the main thing we need is our z-stat. That's our test statistic, is negative 3.06 in 2 decimal places. Then our p-value is 0.0022. So remember what we do is we compare the p-value with alpha. Alpha is 0.05, and our p-value, as you see, is smaller than that, 0.0022. P-value is less, and so then we reject HO. I'll just circle that. So reject HO. And that's our conclusion. So there's enough evidence to reject the claim that the have the same accuracy rates. So let's just summarize that. So I'll just put in a sentence. So I'll say there's enough evidence to reject, right, rather than that, reject the claim that the accuracy rates I'm just having trouble writing today, so are equal at 0.05 significance. Let me just abbreviate that level, significance level. So there's enough evidence to reject the claim. So the claims they're the same or equal. There's enough evidence, statistical evidence, to reject the claim that they are equal. Now here, do you notice we'd actually say about what was better or worse? And certainly from this, it looks like McDonald's accuracy is better, but that's not what that's not what the claim was. So that's not what we're testing. So if you wanted to test one is better than the other, you need to do a different test. Okay, if you want to claim that McDonald's has a better accuracy rate, you can do that test. But you have to do a different claim. The claim he had was that they're equal. And so all we can say is in this test, we can reject that claim that they are equal. Okay. Let's take a look at our second example. Okay, so this one says, in a random sample of males, 23 write with their left hands and 217 do not. In a random sample of females, 65 write with their left hand and 455 do not. Use a 0.1 significance level to test the claim that the rate of left-handedness among males is less than among females. All right, once again, let's take a look at our data for males and females. And so our number of males, let's call it N1, doesn't matter. So it's 23 plus 217, and that should be 240. Yeah, so the number is 240. And then he had the proportion 1. And the question is about left-handedness. So let's do then 23, the rate of left-handedness, 23 out of 240. And that's going to be let's do 3 decimal places in this case. So this can be 0.096. So almost 10%, about 9.6%. Okay. Then for females, are called N2. 65 right with their left hand, 455 do not. So 65 plus 455, and that's 520. And then for left-handedness, so that's 65 out of 520 rather. And then that's 3 decimal places is 0.125, or about 12.5%. All right. Then our alpha in this case is 0.01. Now let's do the same thing again. For hypotheses. And hopefully what you see is in the last one that even though we're testing for 2 proportions, the process is virtually identical than testing for 1 proportion. So we do our hypotheses, we do the p-test, and we make our conclusions. Okay, so once again, our H0 null hypothesis is that the population proportions are equal. And the alternate null hypothesis, HA or H1, this time this is the claim. Let's go back to the claim. The claim that the rate of left-handedness among males is less than among females. So we just call P1, doesn't matter, we just call P1 males. And so that's then going to be P1 portion for males is less than is for females. Okay. Now, if you notice, if you'd done it called females P1 and males P2, then you just say that P1 is greater than P2. That would be an identical test. Okay. So once again, let's go to StatCrunch and plug everything in. All right, so once again, go to stat, portion stats, to sample, once again with summary, then enter what we have. And yeah, I apologize. So this is, yeah, let me go back because I actually should have written this down. Okay, so for males, it's 23 out of 240, and females, it is 65 out of 520. And alpha is 0.01. Okay. All right. Once again, so make sure also your sample one is consistent with the whichever one you called population one in your hypothesis. So for males, it's a 23 out of 240. And then successes is going to be for females is 65 out of 520. Okay. Now here, the question was that let's go back and double check what our hypotheses were. It was that males, the rate of left-handedness among males is less than among females. That was the claim. So P1 is less than P2. So that is equivalent to P1 minus P2 being less than 1, or less than 0. Okay, P1 minus P2, because this case, if that's true, P2 would be larger than P1, and then that would be negative, which would be less than 0. Okay, make sure everything is correct, and then hit compute. Once again, let me copy this into our Word document. Okay, and once again, let's figure out, summarize what we have. Also right over here. So our Z statistic is negative 1.17 two places, and our p-value is 0.1214. Okay, 0.1214. You find that here. Now, so also one thing I'd have room for in the last one, think of this once again as a standard normal distribution. Okay, here with if P1, basic P1 minus P2 is equal to 0 in the middle, and this is that P1 is less than P2, so our p-value is over here. And so once again, we do the comparison. So we compare the p-value to alpha, and alpha was 0.01. So it was a stronger, fairly strong requirement for that. And alpha is 0.01. Then our p-value, as it says, is 0.1214. Clearly the p-value is larger. So once again, what that means is we don't or do not reject the null hypothesis, HO. So once again, what that means, looking back at our hypothesis, we do not reject the null hypothesis. So there's not enough evidence to support this claim that left-handedness among males is less than among females. It doesn't mean that it isn't. We don't know that for sure, but there's just not enough from these two samples. There's not enough evidence to support that claim. That's all it says at this significance level, which that's a p-value is fairly high. So even that would be, we still couldn't reject the claim even like a 0.05 level either. All right, so just summarize this. You can say, so not enough evidence not enough evidence to support the claim that, let's say proportion, summarize that, of, I'll say left-handers or let me say left-handed males, not enough evidence to support the claim that the proportion of left-handed males is smaller than for females. At 0.01 significance level. So let me read that back. So there's not enough evidence to support the claim that the proportion of left-handed males is smaller than that of left-handed females at 0.01 significance level. And once again, that's not claiming, that does not say that that's true for certain, that there is no difference. It just said, once again, based on these two samples, doing this test at this level, there's not enough evidence to support that claim. That it could still be true, we just don't know that. There's just not enough evidence to support it with what we have. Okay, let's take a look at our last example. Also, let me make sure I have enough space. Yeah, I do. Okay, let's take a look at our last example. It says a study investigated the rates of fatalities among patients with serious traumatic injuries. Among 61,909 patients transported by helicopters, 7,813 died. Among 1,061,566 patients transported by ground services, 17,775 died. Use a 0.01 significance level test to claim that the rate of fatalities is higher for patients transported by helicopter. Okay, so I just write H for helicopter and G for ground. Okay, now, so our number, now this time it actually does, in each case, I'll call a helicopter N1, that'll be our first sample, then ground will be our second sample. This case actually does tell us the total number. It says among patients, among this many patients, that many died. So for helicopter transportation, 61,909. And then proportion, P hat, and the question is about rate of fatality. So we're interested in the number of deaths, 7,813 divided by 61,909. And let's divide that and find out what it is. And that comes out to be, let's say, two places. So 0.13, or about 13%. For N2, we have a much larger group, so 161,566. And this is going to be P2 hat. And so out of those, 17,775. And then out of 161,566. So let's calculate that value. And that is going to be about 0.11 to two decimal places, about 11%. And once again, our alpha level, significance level is 0.01. And once again, I just pick the helicopter B population 1, but it doesn't matter. You can do it either way. The same thing, once again, let's do our hypotheses. All right, so once again, our null hypothesis is going to be that both population portions are equal. Then the alternate, H1 or HA, however you want to call it. This, look at the claim again. The claim is that the rate of fatalities is higher for patients transported by helicopter. So our population 1 is helicopters. We're going to say that P1 is greater than P2. So that fits the claim. So once again, let's go to StatCrunch and find out. And once again, let me write these down. Okay, once again, go to stat, proportion stats, to sample, in this case, once again, with summary. Now, so it's plug in. So we're talking about the number of fatalities. That's unfortunately what we call the number of successes. So it's not a success, but for first population was helicopter. So 7813 fatalities out of 61,909 transported. And for ground transportation, ambulance, 17,775 out of 161,566. Okay. Now that's correct in all hypotheses equal to 0. P1 minus P2 is equal to 0. And here we say that, let's double check and look back again. So the claim was that P1 was greater than P2, that the rate of fatalities for helicopter patients was greater than that for ambulance patients. And so this time we want P1 minus P2 to be greater than 0. Okay. And just click compute. And same thing, let me copy these into our Word file. We'll take a look at it there. Okay, and then let's take a look and summarize. This is our stat crunch. Okay, so once again, gives us for count 1 and count 2, make sure the right numbers. So our z-stat, our z is actually quite large. So as you imagine, this is probably going to be rejecting all hypothesis, 10.75. And then the p-value, right, the p-value is much less than 0.0001. Okay, so let's get our comparison for our test. Compare the p-value and alpha. Alpha was 0.01. And the p-value is much less than 0.0001, so obviously that's less. And so we can reject the null hypothesis. Okay, so let's go back at our claim. What that means is that the claim was that significance level is the rate of fatalities is higher among patients transported by helicopter, so there's enough statistical evidence to support that claim that is larger. Though if you notice, though the proportions aren't that different, the one reason why we can reject is because our sample sizes are so large. Now, let's just summarize that. So then we can say there's enough evidence to support the claim of a higher fatality rate for those transported by helicopter. Okay, so there's enough also I should say at the 0.01 significance level. I'd like to include that. Okay, so there's no statistical evidence to support the claim. There's a higher fatality rate for those transported by helicopter than transported by ground ambulance at the 0.01 significance level, although this will probably be valued at even higher significance levels. Now, a couple things to mention. The one thing, I actually call these samples. Now, technically, neither one is actually a sample in a sense, in the typical sense of a random sample in that same way you would take a random sample, but we can probably allow it and actually use that to make conclusions. And also the question is, so what do we take from this? So one question would be why we've got enough evidence to support the claim. So assuming it is true, okay, this is not a guarantee that's true. We just have enough based on this information. There's enough statistical evidence to support the claim at this level. But it could be some reason. So it doesn't necessarily mean that traveling in helicopter is necessarily more dangerous than traveling by ground to the hospital. It could be that people who travel by helicopter were in much worse condition. And maybe that's the reason why they're more likely to die. There could be other reasons, but just keep in mind that here we're simply competing the test and basically saying statistically whether there's enough evidence to reject or not. and or support a claim or not. But the reason why, if there actually is something, if this is actually really true, the claim is actually true, then the reason why it is still a different question. Okay, so what we learned today then is how to test claims about two proportions. As we saw, the process is virtually identical to testing a claim about one proportion. In this case, we did the p-value test. And so once again, you find your test statistic and p-value, use StatCrunch to do that for us, and then compare the p-value to their significance level, and then we reject it or not, then summarize our results. Thank you. Have a good day.